So to address the gearbox reliability challenge faced by the industry, Unreal was fortunate enough to get the funding from the Department of Energy, started this area of research more than a decade ago. It's a consortium, and when we first started, it has testing, modeling analysis, condition monitoring, and database for areas work. The work on condition monitoring has recently shifted to physics data domain modeling for diagnostics and prognostics, which has been planned and executed with reference to prognostics and health management on this slide, which is what we developed. It has two main blocks. One is diagnostics and the other is prognostics. It features data domain and the physics domain information and methodology, also integration of both domains. So it highlights remaining useful life as the output, and the few stars are highlighting the data streams typically available at the wind plant, which will also be leveraged in the present research I'm talking about today. Okay, moving. Okay, sorry, let's see. So my slide is rolling, right?
Yes, we can see it. We're on slide 6. It's what it says in the corner.
Good. So yeah, sometimes these different screens give you headaches, give you confusions. So specific to gearbox bearing fault prediction, we have been targeting bearing axle cracking failure mode. Maybe you have heard of over the years. And another piece of work I'd like to highlight as part of the background for the current presentation is the reliability assessment and the prognosis methodology we developed a few years ago. It's mainly a physics domain method, and we use the data domain information as inputs. So on the chart on the right top, you can see we basically feed the SCADA data through a roller dynamic model and the gearbox model to generate computational to compute frictional energy between the rollers and the raceways. So that's kind of the first step of the whole methodology. And then the next, first, I would say major block is kind of using the computed frictional energy from all individual bearings, and then we get a plant-wide distribution. Also, we get the failure records from the plant. Based on that, we fit a failure distribution and generate a damage threshold. Comparing these two, we calculate or estimate the probability of failures of all individual bearings we are interested in at the plant. So I think that's a methodology. The reason for me to bring this up for the current talk is that some of the variables generated by these physics domain models to look at multiple data streams, including physics domain model data, as I mentioned earlier, developed a few modules supporting this reliability assessment and prognosis methodology. We use those to generate this data. We call this data model data, and also the condition monitoring data. So we try to figure out whether combining all of these data streams together can help us improve the bearing fault prediction performance, right, of these models using these machine learning algorithms at the platform. So that's kind of course, we want to get the better performance. Overall, the methodology, we are following kind of a typical machine learning model development procedure. First, data pre-processing. We get features selected, and then based on those, we can split into training site, testing site, and feed to the model. In between, you have the kind of feedback loop, right? Evaluating the model performance in the end, getting a model acceptable. So next, I will give a detailed walkthrough of one case study, which was published in the 2020 PMI conference.
Sean, I think it would be better if you turn off your video.
And
We're getting a little bit
the
of...
set is about 100 turbines. It's 1.5 megawatt turbines. And there, in total, we got 13 bearing failures in axial cracking. These failures happen to bearings either on the rotor or generator side of intermediate or high-speed shafts. So for the SCADA data, we all know they're at 10-minute average, 10-minute resolutions, and we focus on power, wind speed, and various temperature channels. And by 10-minute resolution, each day we have 144 rows of data recorded by the SCADA. For model data, this is another view. So the process we went through basically look at the feed the SCADA data to the and compare against the status codes, focus on only the running conditions, and go feed them through the Gearbox model, roller dynamic models, and calculate different variables. So the variables include bearing loads, roller deflection, friction energy, sled-to-roll ratios. These are a few examples we have been generating in the model domain. Okay. As I pointed out earlier, we only look at the right. Is that it's not huge enough to make bigger impact in terms of friction energy. And then based on these data, we generated the summary statistics as listed below. So I won't go into the, I want to read the list, okay? So next, we split the data into training and the testing site. We try to be kind of representative. You can see the testing data. There appear to be 3 clusters, and then each cluster we choose one for testing, and the remaining are used for training. So I think in reality, you may be wondering why these 3 are clustered so closely. I thought what happened is maybe they scheduled the bearing repairs around the same time when the crews were available. So it may not represent when the actual failures occur. Okay, that's kind of a caution there. So to label the data as faulty and healthy classes, we basically assumed the last months leading to the bearing repair or replacement at the signature, and all the data are labeled as healthy. You can see that we have a class imbalance issue here between faulty and healthy, right? These algorithms we investigated, they tend to bias towards majority class. So these are kind of their inherent, the algorithm mechanism leads into this. So we need to address this. We look at 2 techniques. I won't go into details either. First one is called synthetic minority oversampling technique. Basically, it generates new samples for the minority class, try to make it balanced, right? So the second is cost-sensitive learning. What it does is if the minority class is misclassified, it gives higher penalty for the algorithm. Hopefully, in the end, it comes to a good balance. So we look at the 4 algorithms: logistic regression, random forest. All of these, if you are doing AI research, you may know already. Extreme gradient boosting and long-short memory networks. Okay. So we added for 3 of these models, LR, RF, and LG boost. We added some line to reflect a little bit recent history in the data, right? For LSTM, it doesn't need to do so since it handles the inherent, the past observations inherently. So for both model, 4 algorithms, all 4 algorithms, we trained and tested on 2 data sets. One is SCADA data only. The other is a combination of SCADA and the model data. Okay. So we adopted practices.
Sean, Sean?
Look at some popular metrics. You have seen the configuration matrix a few times throughout the event already. And then another, also a few other metrics are listed in the table here, a precision recall and the F1 score. We also look at the AUC, that's area under our receiver operating characteristic, the curve here as another metric, okay? So in the result, what we have observed is that how cost-sensitive linear performs slightly better than smooth for these first three models, logistic regress, random forest, and LG-boost. So when model data added to SCADA, the performance increases in terms of F1 score and AUC. So in the paper, we have specific numbers spelled out on the improvement. So as the precision increases, since it's kind of increases F1 score, and F1 score is a combination between the precision and the recall, right? It's a kind of harmonic mean of that. Our LSTM model performs the best. It was not a surprise to us since it was the state of the art. I think still maybe today it's a pretty effective. So we can visualize the results a little bit by comparing the SCADA data only and combining SCADA and the model data performance. This is the confusion matrix. We can see there's improvement on the top rows, right? So basically the true negatives and false positives, but the bottom rows are a little bit of reduction in terms of performance. So for AUC, we can also see that there's a little bit of improvement when we added the model data. So from 0.92 to 0.97. So for the next case study, I can only show a high-level summary since the work is still ongoing. It's from a testing site in North America, 5 turbines, 2 megawatt, 1 planetary, 1 parallel stage, and 3 failed by accident cracking on rotor side bearings. So we got the data for physics domain model development and failure records, right? In the only got of snapshots of vibration data. It's not sufficient to do the fault prediction research as we need it. So we only use oil debris data. And then it has the particle generation rates. If you know that this data sensor, how it works, whenever there's a particle passing the data, they generate a count, right? So we basically use the oil debris data to represent the data stream for condition monitoring. There is a synchronization problem we have to solve. Basically, we read data streams into the shorted lens, that's the oil debris. So we also use the last month as 40 class, the older data as healthy, and we use long short-term memory based on the previous research since it's the best performer. And we use the cost-sensitive linear to handle the imbalance. So this is the results we have got. So it's to our surprise, it's not the best performance. I won't show the other results since it's still ongoing work. What I can say is this is not the best performer among all the cases we look at. So it's a little bit of kind of counter to our intuition. On the other hand, if we look at data fusion research, it also makes sense since when you are combining different things, they may be supporting each other and they may be conflicting to each other, right? These different data streams. So to summarize, case study 1 showed that the model data are potentially beneficial. We need to look at it further. Overall, the fault prediction accuracy can be improved since for that study, we combined the intermediate shaft and the high-speed shaft bearings by normalization approach. So if we can develop models for each, it could potentially help. For case study 2, basically shows us that more data may not lead to the best performance as expected. So we plan to do some feature engineering work. The code can be optimized using the RC curve and That's kind of one more area of work we plan to take on. Also, we assume that when a crack starts developing, it's not known, right, until they're really detectable. So our next piece of work we can look at is by looking at the data, embedded signature stuff, how we can find out the optimal time frame to predict actual crack and the occurrence of the actual cracking in bearings. So these are the references we used. So thank you so much for listening. I will take questions.